Let's illustrate how the PMBM trackers perform in 2 toy examples. To make it interesting, I'm going to make use of the 2 examples that Carl presented when he discussed challenges with using labels to form trajectories. This will enable us to highlight a few simple differences between the 2 approaches. In the first example, we consider a sequence that lasts for 20 time steps. There are 2 trajectories, one that starts at time 3 and ends at time 13, and one that starts at time 8 and ends at time 17. The main challenge in this scenario is that the left object is undetected at time steps 11, 12, and 13. Let us first evaluate a PMBM tracker without smoothing. That is, a PMBM tracker that makes use of the simple approximation to the state densities that are presented in the last video. We use a simple constant velocity model, and the measurement model is also very simple, since there is almost no clutter. The first object is immediately detected at time 3, and then tracked as it moves to the right. At time step 8, we detect the object to the left, and starts tracking both objects. At time step 11, the object to the left is not detected, but our best estimate is still that it is present. We also fail to detect the object to the left at time steps 12 and 13, and our estimator then thinks that the trajectory ended at k = 10. As soon as the left object is detected again, our estimator thinks that the object never disappeared, and then produces a complete trajectory estimate for all time steps. As we continue after that, there are no further misdetections, and we track both objects until they disappear. You may recall that the true trajectories move along almost straight lines, and our trajectory estimate of the left object is less accurate at the times when the object is not detected. You can, for instance, see that the estimated trajectory turns quite sharply at one of those time steps. Let us look at a separate example to try to make sense of what we've observed. For simplicity, we assume that there is only one potential object, and that there is only one reasonable data association hypothesis at every time instance. This means that we can represent the global hypothesis using a single branch, since all other possibilities can be ignored. According to our data association hypothesis, we receive object measurements at time 1 and 2, but no object measurements at time 3 and 4. We may still compute the expected value of x at time 3 and 4, but they are only conditioned on the first 2 measurements. It's also possible that the probability that the object is still there has been reduced, and that our best estimate of the set of trajectories at time 4 is that we have a single trajectory that starts at time 1 and ends at time 2 and takes the values x hat 1 given 1 and x hat 2 given 2 during the 2 time steps when the object is present. I'm assuming here that we are not performing smoothing in the sense that we do not use Z2 to improve our estimate of x at time 1. Suppose now that at time 5, we believe that Z5 is a detection from the same object. In that case, we would realize that the object must be present, which means that it had not disappeared. Instead, we had just failed to detect it at time 3 and 4. Our new estimate of the set of trajectories would then be that we have one trajectory that starts at time 1 and that continues until time 5. As estimates of the state sequence, we could use x hat 1 given 1 to x hat 5 given 5. We note that this estimate is readily available from the quantities that we already compute in a PMBM filter. As you can see, this resembles what we observed in the simulation example on the previous slide. If we want, we can of course perform smoothing and use the measurement at time 5 to try to improve the estimates at earlier time steps. This would require additional calculations, but it's not computationally demanding to do for short time intervals. Let us return to our simulation example and check if this type of smoothing makes a difference for that sequence. As before, we detect the first object at time 3 and the second object at time 8. At the time steps when the left object is not detected, our best estimate is still that the trajectory ended at time 10. As soon as the object is detected again, we produce a complete trajectory estimate also for the left object. As you can see, smoothing helped us improve the trajectory estimate at the time steps when we did not receive any measurements. Still, it's important to note that both of these versions of the PMBM tracker produce trajectory estimates without gaps.